So here we have a standard problem, finding the density function for the ratio of two random variables x and y, where x and y are jointly Gaussian, but with the zero mean, different variances, and they are correlated. So I'll do this explicitly. So starting with FCZ. So first of all, we notice that as x and y goes from zero, minus infinity to plus infinity, z also goes from minus infinity to plus infinity. So the distribution function of z is z less than or equal to z, capital Z. But capital Z is given to be x over y less than or equal to z. Of course, if you can bring this y here, then this will become linear. But the issue is y being Gaussian, it takes both positive and negative values. So the easiest way to deal with things like this is separate out the two cases. So let me call this for the time being A. So I'm going to do A intersection the whole set. Whole set, I'm going to write it as B union B complement. And B, of course, I'm going to take this region, which is y positive. So that's B. And you'll see y. So obviously B complement will be here. This will be B complement. That's y negative. So let me take B to be the event that y is positive and B complement is y is less than 0. So let me expand this. Remember, these two are mutually exclusive. So this is the probability of AB union AB bar. But again, these two are mutually exclusive. So that's the probability of AB plus AB bar, A intersection B bar. So let's write all this a little more. So this is FZZ is probability of AB plus AB bar. And I'm going to substitute for A and B now. So A is x over y less than or equal to z, and B is y greater than 0. So this is x over y less than z, y positive, plus x over y less than z, y negative. Because y is positive, we can bring this up here without with this inequality staying this way. And here, because y is negative, when you bring it here, the inequality flips. So this becomes x is greater than yz when y is less than 0. So we can figure out the two regions where this is and then add it up. So this is the line x equal to y in both, x equal to yz. Depending on the value of z, the slope will be different. And here we need the region x less than yc. So that's this region. This is x less than yc and y positive. Y negative is here and we need x greater than yc. So that will be this region. So if you put these two together, we need to integrate over this region and this region. So this is the line x equal to yc. So that integration is easy because you just integrate on a strip and integrate from. So this will be from minus infinity to yc on x, and this will be from 0 to y. So I'm just going to do that. So this integral is y goes from 0 through infinity, and x goes from minus infinity to yz, fxy, x comma y. First the integral x, then y. And similarly, this integral, that's this integral. This integral will be fxy, x comma y. Notice here x goes from yz to infinity, and y goes from minus infinity to 0, dx dy. So I'm going to, so this plus this gives us FCC. So let me put this up here. So we have FCC equal to minus infinity to, or let's say we'll do the as we had before, 0 to infinity and minus infinity to yz fxy x comma y dx dy plus minus infinity to 0 yz to infinity fxy x comma y dx dy. So now we need to, this is capital FC by the way, the distribution function. So now we need a small FCC, so that's the derivative of the big FCC, the distribution function. So we can do this here by parts. The derivative is inside, so the derivative of this term is the derivative of the upper limit, which is just a y, and substitute the variable of integration yc. So we get fx y yz y dy. That's first term. And the derivative of this 0, then the derivative with respect to z, that's also 0. So basically just this one term. Similarly here, because the first limit's being constant, the derivative goes inside. Then the derivative of the top limit, that's 0. So minus the derivative of the bottom limit. So that's minus y multiplied by, substitute the variable of integration, this quantity. So that will be yz comma y dy. So notice that we can combine these two in this form, because this is in 0 to infinity, y is positive, minus infinity to 0, minus y is positive. So we can write as absolute value of y and then put it as yz y dy. So this much is general. Now I am simply going to substitute for the joint density function, and just to simplify this. So minus infinity to plus infinity, absolute value of y, 1 over 2 pi sigma 1 sigma 2 1 minus rho squared e to the power minus, this is the joint density function of, so instead of x I'm going to substitute yz the whole squared over sigma 1 squared minus 2 rho xy, so that becomes cy squared over sigma 1 sigma 2 plus y squared over sigma 2 squared dy. So we need to, so notice that y, the variable of integration is y, and y appears as y squared here and absolute value of y. So this becomes 2 times the integral from 0 to infinity, 2 cancels. So I'm going to write it as, so FCC becomes 1 over pi sigma 1 sigma 2 square root of 1 minus rho squared. This is just the constant. The 2 went away because the 2 cancellation. Then this becomes 0 to infinity. Now I have y, because no need for absolute value, because this region is positive. And this becomes e raised to minus 1 over 2 1 minus rho squared. And then we have a constant involving z squared over 1 minus rho squared minus 2 rho c over sigma 1 sigma 2 plus 1 over sigma 2 squared y squared dy. So we just need to integrate all this and somehow integrate this out. So let me call this whole thing to be u. So I'm going to substitute 1 over 2 1 minus rho squared multiplied by z squared over sigma 1 squared minus 2 rho z sigma 1 sigma 2 plus 1 over sigma 2 squared y squared to be u. So dy will be 2y dy, 2 again cancel, so I get 1 over 1 minus rho squared multiplied by z squared over sigma 1 squared divided by 2 rho divided by sigma 1 sigma 2 plus 1 plus sigma 2 squared y dy equal to du. So we have y here, dy here. So this whole thing integral for FCC, then we can simplify this as 1 over pi sigma 1 sigma 2 rho squared integral. When y is 0, u is 0. When y is infinity, u is infinity. Y dy is du divided by this constant. And this becomes simply e raised to minus u du divided by, there's a constant, that is z squared over sigma 1 squared minus 2 rho z over sigma 1 sigma 2 plus 1 over sigma 2 squared. So this is at the denominator. This is a constant because integration is with respect to u, and then you have 1 minus rho squared here. So notice that half of this cancels off, giving us this. And I'm going to pull out all these things outside. So we have now FCC. If I haven't made any mistake, this is so far pi is sigma 1 sigma 2. Then you also have c squared over sigma 1 squared minus 2 rho z sigma 1 sigma 2 plus 1 over sigma 2 squared integral 0 to infinity e raised to minus u du. This is 1. So this is the answer. And let's see how much more we can simplify this. So this I can write this as, so I'm going to notice that because of this I can complete the square on z. So I'm going to multiply by sigma 1 squared, sigma 2 squared, numerator and denominator. So I'm going to multiply sigma 1 squared, sigma 2 squared, sigma 1 squared, sigma 2 squared here. So that sigma 1, sigma 2 goes away. And this, so let me, I have sigma 1, sigma 2 square root of 1 minus rho squared because 1 power goes away, divided by pi. Then I have here, once this comes inside, anyway, let me write it down. Sigma squared C2 squared minus 2 rho Z sigma 1 sigma 2 plus sigma plus sigma 1 squared. I'm going to rewrite this as, I just want it to be clear here, only z squared. So I'm going to pull out sigma 2 squared out. So this is sigma 1. And I pulled out sigma 2 squared. So this is 2 rho sigma 1 over sigma 2 z plus sigma 1 over sigma 2 squared. So we can leave it like this, or I can do a little more simplification, because notice that this denominator can be written as z minus rho sigma 1 over sigma 2 squared plus 1 minus rho squared over sigma 2 squared multiplied by sigma 1 squared, this whole denominator. So I can write this as so this whole thing comes out to be of the form some alpha over pi divided by z minus mu squared plus alpha squared, you can see. And this is alpha. So the alpha is, you can see this whole thing can be written as square root of 1 minus rho squared sigma 1 over sigma 2. So alpha is square root of 1 minus rho squared multiplied by sigma 1 over sigma 2. And this is, of course, mu. And mu is rho sigma 1 over sigma 2. And as I said, C goes from minus infinity to plus infinity. So this is a Cauchy distribution centered around the mu. So this is generalized to Cauchy, that's what it is. So I'll write it down in the other page. So FCC is alpha over pi divided by z minus mu the whole squared plus alpha squared, where alpha is square root of 1 minus rho squared sigma 1 over sigma 2, and mu is rho sigma 1 over sigma 2. So, and the shape has this form. It peaks around the mu, obviously. The question is this a PDF? So we can easily integrate this and show that it is. So first of all, the area under this quantity, FZZ. So this is sort of the general Cauchy. So the moral of the story is the ratio of two jointly Gaussian random variables is Cauchy. So FCC DC is alpha over pi square root of minus infinity to plus infinity z minus mu the whole squared plus alpha squared. Notice that if I just a shift in z is not going to change anything, so I can rewrite this as alpha over pi. If I replace z by dz, z minus mu by y, so this becomes, or x, this becomes x squared plus alpha squared dx. Now this is a symmetric function, so I can write this as 2 alpha over pi integral from 0 to infinity 1 over x squared plus alpha squared dx, and substitute x equal to tan theta, then dx is alpha tan theta, so that dx is alpha sec squared theta d theta. So this integral becomes 2 over alpha by pi integral 0 to pi by 2, because when theta is, when x is infinity, theta is pi by 2, and dx is alpha sec squared theta d theta, and the denominator you have alpha squared 1 plus tan squared, which is sec squared theta, sec squared theta. So that sec squared theta cancels, alpha cancels, alpha cancels, you get 2 divided by 0 to pi by 2 d theta. So that's 2 over pi multiplied by pi by 2. That's 1. So z, which is x over y, is Cauchy if x and y are jointly Gaussian. So that's the moral of the story for this problem.